we will explain Chapter 13, Electric Field. In this second video, we will explain electric field lines, and the uniform electric field. We'll start electric field created by a point charge. If we have a point charge which is positively charged, thus electric field will be centrifugal, means coming out from the center of the particle. And if this particle has greater charge, we can represent the electric field more packed, like this. But we can notice that as we go far from the charge, the electric field decreases. So we can see here the electric field coming out from the center. If we bring another particle, but it is negatively charged now, the electric field will be centripetal, coming toward the center of the particle. And if the particle has more negatively charged, the electric field will be stronger, and we can represent it by more packed fields. Also, we can notice whenever we go far from the particle, the electric field decreases. We can see here that the electric field coming toward the center of the particle, which is centripetal fields. Of course, these directions are arbitrary or by convention. Let us see how they implement this convention. They used a test charge which is positive, and they introduce it to the region around the positively charged. As we can see, the positive test charge is repelled by the positive charge we have. And this is how they took the conventional direction of the positively charged electric field. In the same way, they used a positively tested charge and introduced it to the region around the negatively particle. And they noticed that the positively tested charge was attracted to the negative charge. And this is why they used the centripetal conventional direction. So we can define the electric field strength as the force per unit charge experienced by a small positive charge placed in the electrical field. Thus, our equation will be E equal F over Q. F, which is the electric field in Newton, Q is the charge in Coulomb, and E is the electric field in Newton per Coulomb. Similar to this, gravitational field strength is the same, is the force per unit mass experienced by a small test mass placed in the gravitational field. And the equation is gravity equal F over m. F is the gravitational force in Newton, m is the mass in kilogram, and g is the gravity in Newton per kilogram. So if I want to test the electric field strength in this region at this point, we test an electric force. We place a positive test charge. And this red arrow is the electric force experienced by this test charge. So to calculate the electric field strength, we can divide the electric force over the charge of this test charge to get the electric field strength. We can see that as we approach the positively test charge to the positively charged, it is experienced a bigger force. Then the electric field is a region around a charged particle where it can exert an electric force on any charge within the field. As we said, E equal F over Q, electric force over Q. And as we discussed in our first video, electric force equal to K, Q1, Q2 over D square. Here we wrote Q source times Q over R square. Q source is the charge of the electric particle, while Q is the charge of the tested charge we are using, and R is the distance between them, times 1 over Q. So this is the formula of F times 1 over Q. So we can cancel Q by Q, and we will get K Q source over R square. But also, as we discussed in video 1, we can write instead of K 1 over 4 pi epsilon 0, and this is Gauss's law. We can observe from the equation that as the distance increases between the electric charge and the tested charge, the electric field decreases. We can see here if I add a positively charged particle, then the arrow getting dimmer as we go far from the particle. This telling us that the electric field is decreasing as we go far from the particle. Also, if we add a negatively charged, this is centripetal electric field, and also as we go far from the negatively charged particle, the arrow is becoming dimmer and the electric field also is decreasing. Now if we brought a positive charge, then the electric field is centrifugal. What if I brought a positively charged particle within the electric field? it will experience a repulsive force. Then the electric field and the electric force have the same direction. If we bring a negatively charged particle within the electric field, then also it will experience an attractive electric force. Then the electric field and the electric force have opposite direction. If we have a positively charged particle, then the electric field are centrifugal away from the particle. If we introduce a positively charged object, we can see that the electric force and the electric field have the same direction. While if we introduce a negatively charged particle, we can observe that the electric field and the electric force have opposite direction. If we use now a negatively charged particle, the electric field is centripetal towards the center of the particle. And if we introduce a positively charged particle within the electric field, it will experience an attractive electric force. Then the electric field and the electric force are in the same direction. So if Q positive, thus E and F have the same direction. If we introduce a negatively charged particle within the electric field, then it will experience a repulsive electric force. Then electric field and electric force have opposite direction. Here if we have the negative charged particle, the electric field is centripetal toward the center of the particle. And if we introduce a positively charged particle, we can notice that electric field and electric force have the same direction. And if we introduce a negatively charged particle within the field, we can observe that the electric field and the force have opposite direction. If many electric fields act at the same point A, then the resultant electric field at A is the sum of all the electric fields. If I want to check the electric field at this point A, and this is my electric field at point A, what if I put another negatively charged at this place? The resultant changes. Of course, the first one is making first electric field, the second one also making another electric field, and if I introduce a third one, also this one has a third electric field. And the resultant is the red vector, which is the sum of E1 plus E2 plus E3. Now let us discuss the lines of field and the electric spectrum. A field line is a line which is tangent at any point to the electric field vector E. As we already said, the electric field for a positive charge is centrifugal, and the field line will take them tangent to this electric field. That means parallel to the electric field. And we can see here field lines, and which are also centrifugal because we will take the same direction as the electric field. Also, if we have a negatively charged particle, the electric field is centripetal toward the center. Also here we'll take the field lines parallel to the electric field and also in the same direction, centripetal toward the center of the electric charge. By convention, these lines are oriented in the same direction as E, and each one of these is a field line, and the set of field lines we call them electric spectrum. So the electric spectrum is a set of lines representing the electric field. The more closely packed the field lines, the stronger the field is. Now what if we have two electric charges, one positive and one negative? How the electric spectrum will look like? So we can observe here the electric field and the electric field lines coming out from the positive charge into the negative charge. But if we have two positively charged, the electric spectrum will become like this. The electric line going out from the positive charge and also here going out from the positive charge. So here they repel each other and we will see an electric spectrum like this. Also, if we have negative, negative, we will see similar spectrum, same as positive, positive. But in this spectrum, the electric lines and electric field are entering this negative charge and also here entering this negative charge. But here they are repelling each other. Notice that the lines leave the positive charge and enter the negative charge. Here we can see the spectrum for attraction and this one, the spectrum for repulsion. We can observe here when the field lines are more packed, thus the electric field is stronger. Of course, the figure at the left has stronger field, while the figure at the right has weaker field. Look what will happen if we add another positive and negative charge. Let us add another one here to make a line of charges. Another positive here and another positive here. Look what is happening between the lines. The electric field is becoming parallel. Look here, within the two lines in the middle, all the fields are aligned parallel to each other. So if we have these two plates, how we can introduce the electric charges into these two plates, positive and negative charges like this one? By a very simple way, by connecting a battery across the two plates. Then this plate will become positively charged and this one will become negatively charged. And thus we will experience a uniform electric field within the two plates. These electric fields are parallel to each other, equal in magnitude, perpendicular to the plates, and coming out from the positive plate to the negative plate. Thus, the field created between two parallel plates is called a uniform electric field, characterized by all lines are parallel to each other and perpendicular to the plates. As we can see here, all the electric fields parallel to each other and perpendicular to the positive plate and the negative plate. All lines are directed from the positive to the negative plate. This is the positive plate and the electric field is directed from the positive to the negative plate. So here if we have two parallel plates, one positively charged and the second is negatively charged, we will get a uniform electric field starting from the positive plate toward the negative plate perpendicular to the two plates and parallel to each other. So let us check the magnitude of this uniform electric field. We can notice that the voltage across the two plates equal to the voltage of the battery. And as we increase the voltage of the battery, the charges on the plate will accumulate more and more, so the electric field will increase. And as the distance between the two plates increases, the magnitude of the uniform electric field will decrease. So the new rule for the uniform electric field equal to U over D, where U is the voltage across the plates expressed in volt and D is the distance between the two plates expressed in meter. Thus, the electric field E is expressed in volt per meter. Thus, the magnitude equal to U over D, where U is the potential difference or voltage between the plates in volt, and D is the distance between the two plates in meters. So E will be volt per meter. Let us solve this application. Consider two charged particles QA equal to 2 times 10 to the power minus 8 coulomb and QB equal to minus 2 times 10 to the power minus 8 coulomb. Are fixed at the 2 points A and B on the circumference of a circle of center O and radius 10 cm, where OA is horizontal and OB is vertical, given K, Coulomb's constant, 9 times 10 to the power 9 Newton meter square per Coulomb square. Part 1. Determine the magnitude and the direction of the resultant electric field created by the two charges at the center O. Here I draw the circle and the two charges QA, which is the red, and QB, which is the blue. We will start with the expression of the electric field created by QA on O. EA on O equal to K QA over R square UAO. Why UAO? QA is positive 2 times 10 to the power minus 8 coulomb, and we know that positive charges have centrifugal electric field. Then our electric field at O created by A has the direction UAO. This is the electric field created by A on O. R represents the distance between A and O, which is the radius. AO is 10 centimeter, 10 times 10 to the power minus 2 instead of centi, then it's 0.1 meter. So we can plug the numbers. K is 9 times 10 to the power 9, QA is 2 times 10 to the power minus 8 over 0.1 square UAO vector. And the answer of the electric field created by A on O is 18,000 UAO vector, and the unit is Newton per Coulomb. So if we take x-axis along OA to the right and y-axis along OB upward, and since UAO has the same line of action as x-axis but different direction, A on O equal minus 18,000 I. Newton per Coulomb. And why we put minus? Since the electric field created by AO is opposite direction to the x-axis. Now the expression of the electric field created by QB on O equal to K QB over R square UOB. Why we use the unit vector UOB? Since QB is negative charge minus 2 times 10 to the power minus 8. And we already know that negative charges have centripetal electric field. So it's from O to B. So we can draw it like this, in this direction. And this is the direction of the electric field created by B on O. Also R is the distance between O and B, and which is the radius. So it's 0.1 meter. We can plug the numbers. 9 times 10 to the power 9 instead of K. QB is minus 2 times 10 to the power minus 8, but as absolute we will write 2 times 10 to the power minus 8 over 0.1 square. And the answer will be 18,000 UOB vector Newton per Coulomb, the SI unit. As we noticed that UOB has the same direction as y-axis. Thus we can write EB on A equal 18,000 J. So unit vector J is the same as the unit vector UOB, same direction. So the resultant electric field at O will be E resultant at O equal the electric field created by A on O plus the electric field created by B on O. Here no need to make projection since EA on O along the x-axis and EBO along the y-axis. So directly we can plug the numbers. E resultant at O equal to minus 18,000 I plus 18,000 J. And since the two electric fields are perpendicular to each other, directly we can apply Pythagoras theorem. The E resultant at O will be radical EX square plus EY square equal to 18,000 square plus 18,000 square. Of course, the minus is cancelled because it is already square. And the answer will be 25,455.84 Newton per Coulomb. Now we can draw the resultant electric field at O by completing the parallelogram. And here it's a square. This is the resultant electric field. In order to know the direction of the resultant electric field at O, we should calculate the angle beta. Tangent beta is equal to opposite over adjacent. The opposite to beta is the y component of the electric field, and the adjacent is the x component of the electric field. Thus, the direction of the resultant electric field is tangent beta opposite over adjacent equal to EY over EX, which is 18,000 over minus 18,000. Since EX is in the negative sense of the x-axis, it's minus 1. Beta will be tangent inverse of minus 1, which is minus 45 degrees. But here, as we can notice that the resultant electric field in the second quadrant of the circle. So to calculate the angle between the resultant electric field and the positive direction of the x-axis, we should subtract the angle from 180. Thus alpha equal 180 degree minus 45 degree, which is equal to 135 degrees. So alpha is the angle between the x-axis and the resultant electric field. This is the angle alpha 135 degree between the resultant and the x-axis. Now part 2. A point charge Q minus 1 times 10 to the power minus 8 Coulomb is placed at point O. Determine the magnitude and the direction of the resultant force exerted on Q by the two charges. Here, when a charge Q is placed at point O, it is submitted to a resultant electric force. This resultant electric force is equal to Q times the resultant electric field. This formula we can get it from the definition of electric field, which is electric field equal to F over Q. From this equation we can deduce that if Q is positive, thus E and F have the same direction. And if Q is negative, then E and F have opposite direction. Now we will calculate the magnitude of the resultant electric force, which equal to the absolute of Q times the resultant electric field. We can plug the numbers. Q is 1 times 10 to the power minus 8. Of course, Q is minus 1, but absolute it will become 1 times 10 to the power minus 8 times 25,455.84. the result will be 0.000254554 Newton and approximately 2.5 times 10 to the power minus 4 Newton. And since Q is negative, thus E and F have opposite direction. So we can draw it here opposite to E. And this is my resultant force. So we need to calculate the angle theta between the x-axis and the resultant force. But we know that this angle is 180. Thus 180 minus 135, I will get the theta. Thus the angle between the x-axis and the resultant force, theta, equal to 180 minus 135 degree equal to minus 45 degrees. And the negative sign minus 45, since it's clockwise, because from x-axis clockwise negative angle and from x-axis anti-clockwise it's positive angle.